Correlations research. Again, this is Tom West, and in this presentation, we're going to examine a different type of research that isn't really experimental, but still allows us to draw conclusions between and on the relationships between different variables. And in this case, what we're going to see is where we have two continuous variables or more, and the goal is to see how related one may be to another. This type of research does not examine cause and effect. It more so looks at if one measure is high, is the other also high or low, and what that relationship may be. This can be really useful in research in fitness and wellness because often we want to see how important some aspect of physiology potentially impacts some aspect of performance. So let's take a closer look at what we're going to be learning about in this unit. So in this presentation, what I hope to go over for all of you is to understand the term correlation, that the correlation between two variables does not mean causation. It does not mean one thing caused the other. It just means that potentially as one variable goes up, the other one also goes up or goes down. The example I'm going to be using throughout the initial parts of this presentation are height and shoe size. While we wouldn't say that your feet make you taller, we would potentially see that there's a correlation in that taller people tend to have bigger feet. That's not always the case, but it is a potential correlation that could be significant if we examine that type of data. We'll compare and contrast bivariate and multivariate correlations and multivariate analyses. We'll examine the use and the application of bivariate and multivariate analyses, specifically with examples from the research in fitness and wellness. And then finally, we'll talk a little bit about the statistical tests that are utilized to examine the relationship between two variables to tell us how strong is the relationship between the variables and is that relationship statistically significant. So what is a correlation? Again, it's a relationship within a subject between two measured variables. These variables are continuous, meaning that they are not categorical. They aren't just male or female. They are something that's measured along a continuous type of scale. So what we can see here is, again, remember, they're graphed along a y and an x-axis. If you remember from way back in algebra, right, this is the x-axis, and on the x-axis, we have height in inches. So this is 55 inches, 60 inches, and so on. Over here on the left-hand side, the y-axis, we have the size of the person's foot in inches. So what this graph is showing us is each individual person based upon their height and their foot size. So this is a person here. Their foot is 9 inches long, and they're probably 53 inches tall, and so on. And so each one of these dots represents a person. When we put all of those different dots together and we look at them, we can look at, is there a correlation between them? These are all individual people, but in general, do we see a relationship? Do we see that as this measure goes up, height, does foot size also go up? And when we look at this set of dots, we do see that in general, if this number's higher, then this number tends to be higher. There's still a couple examples that are extreme on either end and so on. But we do generally see that if you are taller, you also tend to have a bigger foot and vice versa. It doesn't mean that your foot size caused your height to be taller or vice versa. It just says that they're related. So to some extent, foot size can predict height. Now, that's what we're going to be focusing on in this presentation. I want to look at this concept of correlations between variables. So some definitions. A bivariate analysis, that's just what we looked at on the previous slide. That means two variables. That bivariate means two variables. It describes the direction and the strength of the relationship between two variables. It's called a simple correlation because it is the simplest type. You need at least two variables to do a correlation. A multivariate analysis is another type of, again, correlation, but what it does is it describes the direction and the strength of a combination of variables in predicting a single dependent variable. So sometimes maybe you're interested in, hey, which factor is most likely to make you a great endurance runner? Is it just VO2 max? Is it the tidal volume of your lungs? Is it how much you train per week? All of those are measures that we could take to look at how well you perform later. If we want to look at them individually, those would be bivariate analyses. However, sometimes we may want to look at all of those different variables together in predicting the another variable. So maybe it's a combination of these things that interact to create the best endurance runner. But again, that's the difference. A bivariate analysis or a simple correlation is where we look at one variable and its relation to another. A multivariate is where we look at a group of variables and its relation to some other measure. A regression analysis is like a correlation, and we're going to see examples of this in the literature that I show you. A regression analysis allows us to predict how much one variable accounts for the change in another variable. It says how closely does one measure predict another measure. If the two measures are very close together, as we see in height and shoe size, then we get a very strong regression prediction. We get a very close relationship between them. However, other measures, such as weight and shoe size, do not necessarily predict each other as well. So again, regressions and correlation analysis allow us to see how much one variable can predict another variable. Simple regressions are where we're looking at the prediction of one variable influencing the outcome of another variable. A multiple regression is where we're looking at a combination of predictor variables. Important terms here that you'll see in the literature is one variable often is stated as a predictor variable. That's the measure that we will be able to take and then potentially want to use in some aspect of predicting performance. The predictor variable are the ones that you measure, often are thought of the independent variables, and the variable you're attempting to actually guess at is called the criterion variable. That's the dependent variable. So again, if I was unable to measure people's height, but I could measure their shoe size, I have a ruler, but I don't have a tape measure, I could potentially, if those two variables are closely related, then I could measure people's foot size and from that guess at their height overall. So I could use the predictor variable of foot size to guess their criterion variable if those two variables are very closely related. So make sure you understand, again, we're looking for a predictor variable in some situations to predict a criterion variable. So some elements in correlation research are, again, related to any kind of a research project. Who are your sample? What data do you collect? How do you analyze the data, and so on. So in correlations research, the sample, like in experimental research, is typically randomly selected from a target population. And that allows us to generalize the results. So again, if I'm trying to look at I want to be able to predict height based on shoe size. I want to randomly pick people from the population. I don't want to just pick the tall people or the short people. I don't want to pick just the physically active or the not active. I want randomly selected people. So in correlations research, typically the sample is chosen randomly from a target population. The sample must be of adequate size if our goal is to apply it to the population, just like in experimental research. So the bigger the population, the better in general, although after a period of time, there's less of an advantage to going bigger and bigger and bigger. So generally, though, you do want to have a randomly selected set of subjects from the population. And again, the more you can select and measure, the better. Data collection in this type of research and correlations research can be anything where we're collecting continuous type of data. So this can be from surveys, it can be anatomical measurements, it can be physiological measures, it can be measures of performance, and so on. Typically, it's going to be a continuous measure. However, in some cases, you can utilize ordinal or categorical data within a correlations research, but you'll need to use somewhat different tests to be able to evaluate that. So when you start reading these correlation articles, there are two really important stats or statistical measures that you want to pay attention to. The first is what's called the correlation coefficient. In the case where all of the variables are continuous, which is really the most frequent type of correlational studies you'll see, the correlation coefficient is the letter R. So they'll report an R value. If you have a dependent variable that's ordinal or ranked, then you get Spearman's rho. If it's categorical, you get other measures. One is a phi coefficient, the other is Kramer's V. Really, it doesn't matter. What you just need to know is what the number is. Most cases, like I said, is going to be listed as an R value. Regardless of whether it's an R value or Spearman's rho or whatever, it's going to be a number somewhere between -1 and +1. So correlations are measured. The strength of the correlation is measured on a scale of 1 to -1. Let me explain that a little further. If we go back to this chart here of shoe size and height, this may report, we see a pretty good relationship here. Generally, as height goes up, we see an increase in shoe size as well, right, or foot size. So generally, as one goes up, the other goes up. If it is a relationship where as one number goes up, the other number goes up, then it's a positive correlation. So you'd get an R score that's above 0. It would be a positive number. If the measures all fell right along the straight line here, then it would be a perfect correlation because one would exactly predict the other. If it's a perfect correlation, it would be a +1. It would be an R score of 1. You never see that in real life in natural things. You see something maybe close to 1, a relationship that is really close together, but it's, again, you won't see an actual 1. But the closer it gets to 1, the more closely tied together those two measures are. If we saw the opposite, if we saw a negative line, a line going down like this, where as foot size went up, height went down, that would be a negative correlation, and therefore we would get a negative R score. So we can see on this slide here, the numbers can be anywhere from 1 to -1. The closer it is to 1, the more strength the relationship has. The closer it is to 0, the less strength it has. So generally, if we have an R score or a Spearman's rho or what have you of 0.25 or less, whether it be positive or negative, it would be considered to be a weak correlation. We would probably say it as a weak positive correlation or a weak negative correlation, depending upon whether the R was positive or negative. If it's between 0.25 and 0.49, that's a moderate correlation. If it is between 0.5 and 0.74, that's a moderately strong correlation. If it's between 0.75 to 0.99, that's a strong correlation. And then a perfect correlation is 1 or -1. And again, we say in studies that's not going to happen unless you are truly measuring the same thing. So anyway, that's how we measure the strength of the correlation. And that is done by looking at the correlation coefficient. So again, if we take a look at this example, the shoe size or foot size and height, the coefficient of correlation tells us the strength of the relationship. It tells us, again, somewhere between 1 and -1 is the relationship, positive or negative, and then how strong is it. Another measure that you'll see utilized is a term called the coefficient of determination. This is the degree to which the change in the predictor variable will predict the change in criterion variable. So while the R value tells us the strength of the relationship, the coefficient of determination tells us how much we can use one measure to predict the other. Okay, so one just tells us how related are they. The other says how well do they predict one another. The coefficient of determination is just the R-score squared. So it's the R-score squared, and that gives us the coefficient of correlation. For simple regressions, the R's are considered to be small, they're lowercase. For multiple regression, you'll see it reported as a capital R, but it basically is the same thing, except in a multiple regression, what we're doing is we're looking at how much several variables in combination predict the criterion variable. In a simple regression, where there's an R, small r, it's basically just, again, looking at the relationship between one variable and another. So I've thrown a lot of numbers and terms at you here. Let's kind of look at an example. And again, I'm going to use this same graph that we've been seeing of the size of a person's foot and their height and that relationship. So if we look at this, and again, remember, each of these dots is an individual in our study and shows us, again, where they were. So this individual, they have a 10-inch long foot and they're about 63 inches tall, and so on. So when we look at all of those individuals and statistically analyze them and do a correlation coefficient, we can see how closely these two measures are related to one another. The R for the data in this graph, the correlation coefficient, is 0.622. Okay, so 0.622, what does that mean? That tells us, again, how correlated these two numbers are. So when we go back to this graph, 0.6, or this table, 0.622 tells us that there's a moderately strong correlation. It's a positive number, so it tells us there's a moderately strong positive correlation between the size of your foot and how tall you are. So it tells us that, in general, taller people, we can be very confident that if your foot is bigger, then you're going to be taller. So if we compare shoe sizes and my shoe is smaller than you, you could be pretty confident that you're taller than me because my foot is smaller than you. So again, that's what those numbers tell us. So it tells us how much we can see the relationship between the two. The coefficient of determination is the square of this. So if you take your calculator out, you take 0.6222 and you square it, you get 0.3871. That tells us that the coefficient of determination is 0.3872. That means 38.71% of the variability in height is explained by shoe size. That also tells us that 62% of height is not explained by shoe size. So if we were trying to create a formula that guessed at how tall a person was, one important measure would be foot size, but there are other measures that also can help predict this better. In a multivariate analysis, that's what people would do. They would look at maybe foot size, maybe weight. What else could potentially be utilized? Parents' height, those types of things. We could put a bunch of different variables, predictor variables, into a multivariate correlation to attempt to create a whole host of different measures that predicted even better than 38% of the variability. So again, remember, a correlation coefficient tells us how strongly correlated two variables are, or multiple variables are. A coefficient of determination tells us how much of the variability in one measure is explained by a different measure. So it does say that shoe size has a predictive value for height, saying that if we know a person's shoe size, we can potentially guess their height within a reasonable range. Not perfect, but within a reasonable range. It also tells us that in general, if somebody has a bigger foot, they're going to likely be taller than somebody with a smaller foot. So that's what correlations do. They allow us to examine how closely related different types of measures are. They also allow us to potentially predict performance in a specific test if we know the coefficient of determination. In the book that I've been utilizing throughout this course, they do a nice job of examining a multivariate analysis where they looked at how to predict success in college based upon factors like SAT, high school GPA, and so on. And again, it shows how sometimes one individual variable may not predict very well, but a group of variables can predict performance in some aspect very well. So again, those are how either bivariate or multivariate correlations can be utilized to help predict performance in a specific measure.